This is the second lecture on multi-electron systems. Here we shall lay down the details of the equation to which we are interested in finding solutions to in the upcoming lectures. So, the equation that we are interested in finding solutions to is the non-relativistic, time-independent Schrödinger equation. In other words, we want to find the eigenfunctions and eigenvalues of a certain Hamiltonian. Now, the natural question which arises is, what does this Hamiltonian look like? So, the Hamiltonian to which we want to find solutions to is the molecular Hamiltonian. It has the following terms. The first term is the kinetic energies of the nuclei. The term after that takes care of the electronic kinetic energies. Then we have the term for nucleus repulsion. Then we have the electron repulsion term. And finally, we have the term that takes care of nucleus electron attractions. In this expression, we have made use of the nabla symbol, which is the del2 operator. The del2 operator was given as del2 over del x2 plus del2 over del y2 plus del2 over del z2. Now, the molecular Hamiltonian is usually represented in atomic units, where we set different fundamental quantities to 1 such that the Hamiltonian is rendered dimensionless. So, we set h bar or h over 2 pi, the mass of electron, the electronic charge, and 4 pi epsilon naught, where epsilon naught is the permittivity of free space to 1, and we get the molecular Hamiltonian in atomic units. Now, let us attempt to write the Hamiltonian for the helium atom in atomic units. So first, we have the helium atom. It has a nucleus and two electrons. It has a nuclear charge of Z equal to +2. Now, if we look at the first term, we have to write the term for the nuclear kinetic energy. Which in this case would be then we have the electronic kinetic energy. We have two electrons. So we shall have two terms. One for each of them. After that, we have the nucleus-nucleus repulsion term. But helium is an atom and it has only one nucleus. meaning that this term does not exist for the helium atom. After that, we have the electronic repulsion term, which in our case be given as minus 1 by R12, since we have two electrons, and R12 is the vector connecting the two electrons. And finally, so this should be a plus since it's a repulsion term. And finally, we have the nucleus electron attraction term, which in our case is given as minus 2, since the charge on the helium nucleus is 2, by capital R to denote it's a distance between the nuclei and an electron, or it's a distance that takes care of, or it's a distance that is composed of, or that pertains to the nucleus, and hence we use capital R, and since we have just one nucleus, we use Roman numeral 1 followed by the attraction to the first electron, and we shall have another term minus 2 by capital R Roman numeral I 2 to denote the attraction for the second electron with the nucleus. In this Hamiltonian, it is interesting to note that if we did not have this term, that is the electron-electron repulsion term, we could separate the variables. Note that we are considering the nucleus to be fixed, hence this term would be rendered a constant. And as we had seen in the previous lecture, the eigenfunctions for the system, if we did not have the electron-electron repulsion term, would look like psi1 times psi2, where psi1 is an eigenfunction of the Hamiltonian composed of just the variables of the first electron, and psi2 is an eigenfunction of a Hamiltonian composed of just the second electron's variables. So, the helium atom is a nice segue to perturbation theory, because what it essentially does is to break the Hamiltonian into two parts. That is, one part which has exact solutions, and the other part which renders the Hamiltonian insoluble. So, what we can do is to call this part of the Hamiltonian, that is, the component Hamiltonians without the interaction term, the exactly soluble Hamiltonian. And this part of the Hamiltonian as the perturbing Hamiltonian, and helium atom is interesting because it has the perturbing Hamiltonian of the simplest type, that is just one electron-electron repulsion. In the next lecture, what we shall see is how do we go about applying perturbation theory to find the solution of the helium atom. Thank you.